Thank you, and good afternoon. It's my great honor to be here to share our recent work with you. And my name is Juhao Su, and I'm an MPhil student, which is short for Master of Philosophy student from Hong Kong University Science and Technology. I was also co-supervised by the Hong Kong Center for Construction Robotics. So today I'm going to share our recent research related to MPC, which is Model Predictive Control based strategy of this swing attenuation. And to be start, I will let you know about the background of this project. So during our investigation of the automation solution in construction industry, we find that there is an emerging construction approach called MIC, which is modular integrated construction. So this method utilizes the off-site manufacturing and on-site assembly. So this kind of method have the sustainability benefits like centralized pollution treatment, and it will enhance the standardization and will reduce the waste. So also this method is very efficient, and in areas like Hong Kong, the rental cost of tower crane or labor is very expensive. So this kind of method is game changing recently, and we were seeking if we can do some automated solution in this area. And the module used in this MIC is something like this. It has full furniture, and there are mechanical equipment, electrical devices already installed. So it needs very careful treatment during the transportation and installation. And it needs to be precisely positioned during the installation because there are some structural components need to be anchored. So the traditional way to do this is that we call some workers on site. They will, some of them will observe and give command, and some of them just form a circle and use ropes from different direction to drag the frame. So this kind of work is labor intensive and very skill dependent. And also the operation, the lift operation is also a skill dependent work in Hong Kong. So we try to do something in this area, and we find out that actually there is a pity that no matter what kind of crane, no matter overhead or a rotary tower crane or mobile crane, they exist some commonality in the dynamic problem. They only have 3 actuators, but the payload actually have 6 degrees of freedom to be controlled. That is XYZ position, roll pitch yaw orientation. So this kind of system is considered as underactuated system, also known as non-suggestion. So and also in the real scenario, it's not like moving a robot arm or a rigid stick. So the tower crane move, but the payload will have some kind of delay in movement. So it will rotate near the center of this hook. So it will be a multiple pendulum system with the characteristic of nonlinear and coupled. So there are some research in this area already. The first one is the very famous zero vibration input shaper. It uses a delayed input to cancel out the residual swing. And the second one, dynamic included trajectory, use the system dynamic to do something like this vibration, but more continuously. And the second stream is the closed loop feedback control. So we have many advanced controllers. The first one, sliding mode controller, is very robust toward those uncertainty and disturbance. And this model predictive control can predict the system behavior and can impose some constraint toward the system state. And fuzzy logic control can incorporate some human-like reasoning process in the control. But there is a gap that seldom of them consider double pendulum effect. Although they use very advanced controller, they only consider single pendulum, or some of them consider double pendulum, but they only consider the movement control and Gibbs-Lewis control. So we think out of the box. We were trying to explore some auxiliary input to rendering the dynamic fully actuated. And for this paper, we will go further about this. but it's an ongoing project. Currently, we were doing something in 2D space, and it can be expanded to 3D, or maybe in the future, it can be scaled up. So we have to make some modification toward the conventional component. This is a conventional hook from Crane system, and we add two propellers in our scaled model. So this propeller will generate an opposite direction thrust, and the composite force will impact the hook and the payload here. So it will be simplified as the double pendulum model here, and we can see that actually the mass, the rope length will affect, and the trolley acceleration will affect the system. This theta 1 and theta 2 is the swing angle here and here. And we use the equation here to develop a state space system here. We then apply the Model Predictive Controller, which is running on a digital system, which is also known as discretized system. So it will predict the system behavior in like future 10 or 20 steps. And it will generate a reference line here. So it's approaching the desired reference state. And also it will do the optimization for the future period. We only take the first input as our exact system input. And during our simulation, we find that if we have a very smooth transition of the trolley, and if we don't have such a proactive method, it will free swing like this to up to 5 point something degree. But if we add some proactive swing control, no matter it's LQR, linear quadratic regulator, or sliding motor controller, or MPC, it can control the system behavior well at constantly 0. But we all know that the condition is not always ideal. So this simulation compare the condition with some delay. We all know that the estimation of the hook state and also the control allocation to achieve the target value takes some time. So we consider some delay and compare the performance between the among these three controllers. And then we can see that MPC actually outperform others because in the predictive function, we can offset the delay. And we also wonder that what if the propeller cannot provide sufficient thrust to the system that we need. So this time we consider the actuator saturation, and we increase the mass of the payload to test that whether the controller can still maintain the system's stability. So this time from the result here, we can see that MPC, again, we outperform others. The input curve here is very smooth without sudden drops because it can predict before the actuator saturation actually happen here. And for a very short conclusion here, we have verified the effectiveness of this proactive swing control method, and we verified some kind of resilience to uncertainty and undesired condition. And in the future, we will add some disturbance observer because MPC is quite relying on the very precise internal dynamics. So we need a disturbance observer to compensate those undesirable external disturbance. And also we will conduct more intricate experiment to verify the performance of this disturbance observer. And we also will need to extend our simulation and experiment to 3D rotary tower crane. We have already built the platform here. And here I will show a short demo video of this overhead tower crane. So it overlaps two videos. So one is, sorry. All the movement pattern is identical, but we can see that we have some kind of improvements in performance. One is propellers off and one is propellers on. And it's not perfect because in our lab environment, there are some kind of latency because all these platforms running on ROS, and we use a motion capture system to get the state of the the component. So it maybe some latency, and we are trying to figure this out. And you may see that we have our bigger rotary 3D tower crane there. So we will do the experiment very soon, and hope to share with our more information in this year or next year through our journal paper here. And you may see that we have an unmanned ship here. It's for dock area and bridge pier area for the crack inspection. And also this center provide more single task robot doing more construction work. So, sorry, please feel free to Google HKCRC, and we can have more cooperation or information exchange. Thank you.